Now the thing to realize is that a balanced chemical reaction is a recipe that allows us to get from reactants to products. Here is a chemical reaction that's balanced for the reaction of nitrogen and hydrogen to go to ammonia. In this case, 1 mole of nitrogen and 3 moles of hydrogen go to 2 moles of ammonia. And we could also express this as 1 molecule of nitrogen and 3 molecules of hydrogen goes to 2 molecules of ammonia. For us, it's going to be much more convenient to talk about moles because now we're working in the macroscopic regime. We're talking about stuff that you can weigh, ultimately, in the laboratory, and so moles is going to be more convenient. Now, I'm going to guess that if this said 1 cup of milk and 3 scoops of ice cream to make 2 milkshakes, that you'd have absolutely no problem with any of the concepts that we're going to talk about here. And that analogy is absolutely perfect. In other words, we could ask the question, if we had 1 cup of milk, how many scoops of ice cream do we need? Well, you'd answer 3 scoops of ice cream. And if I said if we had 2 cups of milk, how many scoops of ice cream would we need? You'd immediately say 6 scoops of ice cream. And there is no difference between our chemical reaction as a recipe and our recipe for milkshakes. Try to keep that in mind, and I think you're going to find these problems much easier to get your mind around. So here's an example. How many moles of nitrogen are required to react with 3 moles of hydrogen? And if you go back to our balanced chemical reaction and think about it in terms of milkshake or think about it in terms of moles, you'd immediately say we need 1 mole of nitrogen to react with 3 moles of hydrogen. And similarly, if we have 6 moles of hydrogen, then it would require 2 moles of nitrogen. So that's your intuition working, and that works great. But suppose now we have 8 moles of hydrogen. How do we mathematically express the idea that of how many moles of nitrogen do we need if we have something that's sort of not easy to convert in your head? And the answer is that we relate the number of moles of nitrogen needed to the number of moles of hydrogen that we have times a conversion factor that comes from the balanced reaction. And we want the thing that we want to cancel out. In other words, we want to cancel out moles of hydrogen, so we put moles of hydrogen in the denominator, and we put moles of nitrogen in the numerator. And where do the 1 and the 3 come from? The 1 and 3 come from the balanced reaction. So let's look back at the balanced reaction. Okay, here's a 3, here's a 1, implied 1, and it's 3 and 1. Now let's double check and make sure that this works for A and B that we understand intuitively. If we have 3 moles of hydrogen, then according to the balanced reaction, or this reaction here, then we need 1 mole of nitrogen. That works great. We already agreed with that. If we have 6 moles of hydrogen, plug in 6 moles here and work out the algebra, and we need 2 moles of nitrogen. Works great. If we have 8 moles of hydrogen, how is this going to work? We'll see that on the next page. Before we go on, let me remind you that these numbers here, the 1 and the 3, these are exact numbers. So these don't limit your significant figures. So don't worry about the fact that it's not 1.00 moles, 3.00 moles, or something like that. These are exact. All right, so let's look at 8 moles of hydrogen. And using the formula on the previous page, 8 moles of hydrogen times 1 mole of nitrogen over 3 moles of hydrogen, and we get 2 2/3 moles of nitrogen. Here I assume that 8 moles was an exact number, and so I express this as a fraction. More often you're going to have something with a decimal point like 12.7 moles of hydrogen, and again, use the conversion factor, and we get 4.23 moles of nitrogen required to react with 12.7 moles of hydrogen that we started with. And this is to the correct number of significant figures. Because we have 3 here, we need 3 here. All right. Now, we can use the balanced reaction to figure out how much product we're going to make. How many milkshakes can we make given a certain amount of milk and a certain amount of ice cream? For instance, how many moles of ammonia can we expect from 9.4 moles of nitrogen or 13.3 moles of nitrogen, assuming that we have enough hydrogen to react with all the nitrogen? Right? It'll become clear why we have to make that assumption in the next tutorial, but basically what I'm saying is, suppose you have enough ice cream and you're just worried about how much, if you have tons and tons of ice cream and only a little bit of milk, how many milkshakes can you make? And the equation is that the moles of ammonia expected is equal to the moles of N2 that you started with times the conversion factor, and the derivation of this conversion factor is exactly the same as we use for hydrogen and nitrogen, except that since we can make 2 moles of ammonia for every mole of N2, it's a 2 over 1 instead of a 3 over 1. Remember, 3 over 1 came from the fact that we need 3 moles of hydrogen for every 1 mole of nitrogen. Okay, so we're going to use this expression. 9.4 moles of nitrogen times 2 moles of ammonia for every 1 mole of nitrogen gives us 19 moles of ammonia. And 13.3 moles of nitrogen times 2 moles of ammonia over 1 mole of nitrogen gives us 26.6 moles of ammonia. Okay, pretty simple. We used the same idea twice. The first time we were worried about how much hydrogen do we need, how much nitrogen do we need for the amount of hydrogen we had, and then the second time, how much ammonia can we make for a certain amount of nitrogen we have. Okay, now unfortunately, scientists haven't come up with a way to weigh in moles. And the way we weigh things, or determine the mass of things, is we use a balance, and balances always give you things in grams. And so in order to do what we just did, remember, absolutely everything has to be in moles. I can't emphasize that enough. Absolutely everything has to be in moles. Everything has to be in moles. Everything has to be in moles. So you have to do things in moles. How do you get from grams to moles? Well, to get from grams to moles, you divide by the molar mass, convert everything into moles, and then use the balanced reaction and then convert back to grams. So for instance, how many grams of H2 do we need to react with 53.1 grams of N2? And again, the procedure is convert everything to moles. So what we need to do is convert this into moles, and then use the balanced reaction to figure out how many moles of hydrogen we would need, and then ultimately convert the number of moles of hydrogen we need back to grams. Okay? So three-step process instead of a one-step process. And the key is moles, moles, moles. It has to be in moles. All right, so three-step process. First, we figure out how many moles of N2 we have. It's 53.1 grams times the conversion factor for the molar mass of N2, which is 1 mole over 28.0 grams. So that gives us 1.9 moles. This is 1.9 moles of N2. Let's put that in to remind us. And then moles of hydrogen required, and I recommend going ahead and labeling what your calculation is going to be. So moles of H2 required. Now we use the balanced reaction. It's the number of moles of nitrogen, which is 1.90 moles, and this is moles of N2, times the conversion factor, which we used much earlier on. 3 moles of hydrogen for every mole of nitrogen means that we need 5.70 moles of hydrogen to react with our 1.90 moles of nitrogen. And then convert back to grams. Remember, three-step procedure. So the mass of hydrogen required is 5.7 moles of hydrogen, okay, moles of H2, times the molar mass of hydrogen, which is 2.02 grams, divided by 1 mole, okay, grams per mole. And that gives us 11.5 grams. So this is the mass of hydrogen that we would need to react with 53.1 grams of nitrogen. So what have we learned? We've learned that we can use the balanced reaction as a recipe in moles for determining how much of one reactant we would need given the amount of the other reactant. And similarly, we figured out how much product we could expect in moles based on the amount that we have originally in moles. So moles, moles, moles. The balanced reaction's in moles, and you can use it to get from reactants to products or to figure out how much of one reactant you need given the amount of the other reactant.